Okay, introduction. Okay, string theory is a physics theoretical framework aimed at describing the fundamental nature of particle and force in the universe. Okay, it's implied that the fundamental building block of matter are small vibrating string of energy rather than point-light particle. One of the most exciting part of string theory is the idea that our world may have more dimension than the usual two. Here are two important aspects to remember about string theory and multiple dimension. Okay, the first one is extra dimension. According to string theory, the universe has more dimension than the three we are familiar with, that is length, width, and height. Okay, there could be extra compositive dimensions that are curled up and hidden at a microscopic scale. According to the notion, these extra dimensions are not readily visible in our daily life, but they play an important role in the behavior and property of string. Okay, the second one is the consistency and unification. Okay, string theory has the ability to unite the fundamental force of existence, including its gravity, electromagnetism, and the strong and the weak nuclear force. Okay, it provides a mechanism to reconcile the principle of general relativity with quantum physics by introducing gravity into the quantum mechanical framework of string theory. Okay, this unification is a significant objective in theoretical physics and may lead to more comprehensive knowledge of the cosmos. That's all. Thank you.
Experimental testing of string theory and multiple dimensions is a challenging task because many aspects of the theory cannot be directly tested with current experimental technology. However, there are several approaches that have been taken to try to test and understand string theory and extra dimensions. First, particle physics experiments. While the energies required to direct, produce, and detect the effects of strings or extra dimensions are currently beyond experimental reach, there is research being conducted on the constituents and predictions of string theory that can be tested through high-energy particle experiments. Second, cosmological effects. String theory and extra dimensions can also impact our understanding of cosmology, the origin of the universe, and the nature of dark matter. Third, gravitational effects. String theory aims to unify gravity with quantum mechanics. In certain cases, string theory can yield predictions for gravitational effects on scalars different from Newtonian gravity or Einstein's general relativity. Lastly, holography. The holographic principle in string theory, such as the ADS or CFT correspondence, provides the way to relate string theory in certain dimensions to lower dimensional conformal field theories. Well, to date, there is no direct experimental verification of string theory and extra dimensions. Indirect research and testing are continuously being pursued in various fields of physics, including particle physics, cosmology, and gravity. The aim is to understand the fundamental nature of the universe and validate or refine string theory.
Hello, so my name is Muhammad Afiq bin Kirori, and I will presenting the application of string theory and multiple dimension. So for the first one is fundamental particle physics. String theory unifies particles and their interaction by considering them as tiny vibrating string instead of point-like objects. It also incorporates extra dimension to explain particle properties and forces. Quantum gravity. String theory is a leading candidate for a quantum theory of gravity, aiming to reconcile gravity with the other fundamental forces. By incorporating gravity into the quantum mechanical framework, it offers a potential path toward a unified theory of all natural forces. For the third one is cosmology and the Big Bang. String theory impacts cosmology, providing explanation for the early universe, including the Big Bang, and suggesting a higher dimensional multiverse that addresses cosmic inflation and other cosmological puzzle. So the one, the black holes. String theory shed light on black holes, suggesting that have a microscopic structure and that information is preserved on their event horizons. It has advanced our understanding of black hole entropy, thermodynamics, and connection to the other branches of physics. Condensed matter physics. String theory techniques find application in condensed matter physics, helping researchers understand strongly uncorrelated systems that inhibit behavior similar to black hole or extra dimension.
So next is limitation. String theory is theoretical framework that attempt to unify all fundamental force and particle in universe by modeling elementary particle as tiny vibrating string. While string theory has many promising features, it also has certain limitations. So first of all is lack of experimental verification. One of the primary challenges of string theory is the lack of experimental evidence. Since the energy required to directly probe the scale at which string-like behavior becomes significant are currently beyond our technological capabilities, it is challenging to test the theory through experiment, and this makes it difficult to confirm or refute its prediction. Second is landscape solution. String theory predicts the existence of vast number of possible solutions, often referred to as the landscape. The landscape of numerous universes entangle the effort to create particle physics theories under string theory. This solution corresponds to different configuration of extra dimension and the properties of the strings. While this feature provides a wide range of possibilities, it also makes it challenging to select a specific solution that describes our observed universe. Third is complexity and calculational difficulties. String theory is mathematically complex framework that involve sophisticated mathematical techniques such as advanced geometry and algebraic structure. So this complexity makes it challenging to perform calculation and make concrete prediction. As a result, it is difficult to explore the full range of phenomena that could emerge from string theory. And lastly, compatibility with general relativity. The entire theory does not have consistent definition in all scenarios. Even though string theory is often held as theory of everything, it still struggles to combine quantum physics and general relativity into single universe theory.
Hello everyone, my name is Jack Nicholson John, and today I will give you a quick glimpse into the fascinating world of string theory and multiple dimensions. String theory proposes that the universe's fundamental building blocks are tiny, vibrating strings, and not particles. It goes beyond our 4 dimensions and suggests the existence of extra dimensions. Researchers explore string compactification, where extra dimensions are curled up in tiny shapes, explaining why we observe only 4 dimensions. And next, the landscape of spring theory predicts numerous vacuum states, each representing different physics. Selecting our observed universe from this vast landscape is an active research area. String duality connects seemingly different theories. For example, the ADS or CFT correspondence links string theory to conformal field theories. Exploring this connection shed light on both string theory and other physics. The scientists study string theory's implications for particle physics and cosmology, aiming to explain observed phenomena and make testable predictions. Mathematical foundations such as algebraic and differential geometry provide insight into string theory. And in summary, string theory and multiple dimensions captivate researchers, pushing the boundaries of our understanding. Thank you everyone. Masya.